All right, let's dive in. Today we are going deep into a document most of you are familiar with, at least in passing.
Oh, yeah.
The Biosafety in Microbiological and Biomedical Laboratories.
That's right, the BMBL, 6th edition.
That's right, the BMBL 6th edition. We'll just call it the BMBL for short.
Cookies. Everybody does.
So this document is kind of like the rule book for anyone working with microbes and other, biological materials that could be...
Yeah, the hazardous stuff?
Yeah, the hazardous stuff in a lab setting.
Yeah.
In the U.S.
Absolutely. It's the overarching guidance for biosafety practices in the U.S. It really sets the standard for how to safely handle and contain these infectious microorganisms and any hazardous biological materials. It covers the gamut.
And just for context, this isn't, some brand new thing. This has been around for a while.
Right. The BMBL has been around for decades.
So when did it first come out?
The first edition was way back in 1984.
Wow, okay.
And even back then, they nailed down the core principles that we still follow today.
What would you say those core, most important things are?
2 biggies: containment and risk assessment.
Containment. Okay, so that makes sense. I mean, you don't want this stuff getting out.
Right.
But what does containment actually look like when you're in the lab?
Well, think of it as a multi-layered approach. It starts with those everyday practices, the techniques that every microbiologist learns, how you handle cultures, how you dispose of waste.
Right. So basic lab hygiene.
Exactly. Then it extends to those specialized pieces of equipment that provide physical barriers, like those biosafety cabinets, the ones with the airflow.
Yeah.
And it even goes as far as the facility itself, how the lab is designed and engineered, the ventilation systems, the controlled access areas, all working together to minimize the risk of anything escaping.
Okay, that makes sense. And then the other big one you mentioned, risk assessment. How does that fit in?
Risk assessment is where you really need to think critically about what you're doing in the lab. It's a systematic process for identifying hazards and evaluating the potential risks associated with those hazards.
So it's like, how likely is something bad to happen? And if it does happen, how bad could it be?
Exactly. You have to consider both the likelihood of something happening and the potential consequences if it does. You identify the hazardous characteristics of the infectious agent or the material you're working with.
Okay, so figuring out what makes it dangerous.
Exactly. Then you pinpoint the activities that could lead to someone being exposed in the lab, and then you have to weigh those 2 things. How likely is it that a lab-associated infection, or LAI, would actually occur? And if it did, what would be the potential consequences?
So the severity of the infection.
Right. And all of that informs what level of precautions you need to take.
So the BMBL isn't just about, here are the rules, follow them blindly.
No, it's not a one-size-fits-all approach.
It's more nuanced than that.
It encourages you to tailor your safety measures based on the specific risks you've identified.
Right, because obviously working with, a common, relatively harmless bacteria is going to be different from working with, something much more dangerous.
Exactly. And the BMBL is constantly evolving. It gets updated periodically to incorporate new scientific knowledge, lessons learned from incidents, and to address emerging threats. That's why we're on the 6th edition now.
That's impressive.
It really shows how seriously they take keeping this information relevant.
So who are the masterminds behind this constantly evolving document? Who puts all of this together?
Well, it's a pretty massive collaborative effort. A lot of really smart people contribute their expertise. You've got scientists who are working in labs every day, and you've got lab directors who are responsible for overseeing those labs and making sure safety protocols are followed.
Yeah.
Occupational physicians who understand the health risks. Epidemiologists who track diseases. Public health experts who are looking at the big picture. And of course, biosafety professionals who are dedicated to making labs safer.
It's a team effort.
It really is. You need all of these perspectives to create a comprehensive and effective guide.
And the outline even lists some of the people who contributed to this latest edition.
Yeah, just to give you an idea of the breadth of knowledge involved, folks like Susan Lawrence from the EPA, Susan Lippold and Carolina Luquez from the CDC, R. Trevor Lubbert from NIH, Sigirin Pillai from the FDA, Jeffrey Potts, and Deborah Wilson, also from NIH. We also had Nathaniel Powell Jr., a vet from the CDC, Stephen Tomasino from the EPA, Elizabeth Wyrick from the CDC, and David White, a vet from the USDA. And let's not forget Shana Mangino and Dr. Mallory Polmios from Eagle Medical Services, who did a ton of the organizational and editorial work to pull this huge document together.
It sounds like a real who's who of the biosafety world.
It really is. And it makes you realize how much thought and expertise goes into this document.
So what are we hoping to accomplish today with this deep dive into the BMBL?
Our goal is to distill the key insights from this massive document, focusing on the most important aspects of lab safety, the process of biological risk assessment, and that often overlooked area of biosecurity.
Right.
We want to equip you, the listener, with a practical understanding of these critical areas so you can apply them in your own work and be even more vigilant about safety.
All right, let's do it. Let's kick things off with that foundation biological risk assessment. Why is that considered so essential in the BMBL?
Biological risk assessment is absolutely fundamental to safe lab operations. And the BMBL really drives that point home. It emphasizes that this is not just a box-checking exercise. It requires careful, informed judgment. And it stresses that the primary responsibility for this lies with the lab directors and the principal investigators, or the PIs as they're often called. They're ultimately accountable for safety in their labs.
It makes sense. They're the ones running the show.
Exactly. But it's not just their burden to bear alone.
Right. The outline mentions some other groups that are involved.
Yeah, it's definitely a collaborative effort. The BMBL highlights the roles of institutional biosafety committees, or IBCs, the animal care and use committees that oversee animal research, biosafety professionals who provide expertise, occupational health staff who are looking after the well-being of the lab personnel, and even the lab animal vets.
So a lot of different stakeholders. And is it just those official experts who have a say in risk assessment? Or should other people be involved?
Oh no, the BMBL really emphasizes the importance of including a broad range of people in risk assessment reviews. This means involving the lab staff who are actually doing the experiments, as well as any other subject matter experts who might have specific knowledge about the agent, the procedures, the equipment, or whatever else might be relevant.
So getting that frontline perspective.
Exactly. Their input is incredibly valuable.
Okay, so we figure out who needs to be at the table. What are the actual steps involved in conducting a biological risk assessment?
The BMBL outlines a pretty straightforward process. There are 4 main steps. First, you need to identify the hazardous characteristics of the infectious agent you're working with.
Right. So figuring out what makes it dangerous in the first place.
Exactly.
Right.
How does it cause illness?
Right.
How is it transmitted?
Yeah.
Next, you need to determine which specific activities in the lab could lead to someone being exposed to that agent. What are those potential points of contact?
Yeah.
The third step is to assess the likelihood of an LAI, that lab-associated infection, actually occurring, considering those potential exposure routes.
Oh.
How likely is it that someone will actually get infected?
Okay.
And finally, you evaluate the potential consequences of an infection. If the one does get infected, how bad could it be? What are the potential health effects?
So we've identified the hazard, looked at how exposure could happen, figured out how likely that exposure is, and then thought about how bad it would be if someone did get infected. Then what? What do we do with all of that information?
That's where the rubber meets the road. The results of your risk assessment directly inform what safety measures you need to put in place.
Okay.
This includes determining the appropriate biosafety level, or BSL, for the work, deciding which specific microbiological practices need to be followed, what safety equipment is necessary, things like biosafety cabinets, personal protective equipment,
Right.
and also what facility safeguards are required. Things like specialized ventilation systems or limited access areas.
It sounds like risk assessment really needs to be integrated into the everyday culture of the lab.
That's exactly what the BMBL emphasizes. It stresses the need to create a strong safety culture. It's not just about following a checklist. It's about making risk management a part of daily lab operations. It means everyone is constantly thinking about potential hazards, identifying those high-priority risks, and then developing and implementing specific ways to mitigate those risks.
Okay. And when we talk about mitigating risks, are there different levels of controls that we should be thinking about?
Yes. The BMBL talks about the hierarchy of controls, which is a really useful framework for thinking about how to manage risks effectively. It starts with the most effective methods and moves down to the least effective. The most effective is elimination. If you can get rid of the hazard altogether, that's obviously ideal.
Right. But that's not always possible.
Often it's not. The next best thing is substitution. Can you use a less hazardous alternative? If you can't eliminate or substitute, then you move to engineering controls.
So physical changes to the workspace.
Exactly. Things like biosafety cabinets, ventilation systems, interlocks on doors. Then you've got administrative controls, which are essentially the rules and procedures you put in place.
Okay.
Things like training programs, standard operating procedures, signage. And finally, you have personal protective equipment, or PPE.
That's the last line of defense.
It is. Things like gloves, lab coats, respirators. PPE is important, but it should never be your only control measure. You should always try to work your way up that hierarchy first.
So before we even get to someone needing to put on a respirator, we've already done everything we can to minimize the risks.
Right. Multiple layers of protection.
Okay, that makes sense. Now, where do you even begin when you're trying to figure out the risks associated with a particular agent? Where do you get that information?
The BMBL itself is a great place to start. Section 8 has summary statements for a whole bunch of agents that are known to cause LAIs or that are significant for public health. These statements provide a lot of useful information about those specific agents, including details about how infections happen in the lab, how much of the agent it takes to cause an infection, how stable it is in the environment, whether there are effective vaccines available, and other relevant factors.
Oh, wow. So it's like a little mini dossier on each one.
It is. It's really helpful. And the Public Health Agency of Canada also has these great pathogen safety data sheets. They're freely available online, and they go into even more detail about a wide range of pathogens.
So those are good resources.
Yeah, they are. And of course, it's always a good idea to talk to people who have experience working with the agent you're going to be using.
Right. Get some first-hand knowledge.
Exactly. Consult with colleagues, mentors, biosafety professionals. They can provide a lot of valuable insights.
Now, the outline mentions aerosols and droplets specifically. Why are they highlighted as such a concern?
Aerosols and droplets are a big deal in the lab because they're kind of insidious. They can be generated so easily during many common procedures, and often you don't even realize they're being produced. They can also spread really easily through the air, potentially exposing not just the person doing the work, but also anyone else in the lab. There's a lot of evidence suggesting that aerosols and droplets are a significant source of lab-acquired infections, especially in cases where the only known risk factor was just being present in the lab where the agent was being handled.
It's like an invisible enemy.
It is. And that's why it's so important to be aware of the procedures that can generate them and to take steps to minimize their production.
Okay, now the BMBL is a guidance document, but are there any specific regulations that it ties into?
Yeah, while the BMBL itself isn't a law, it's important to keep in mind that your institution's biosafety plan, which is based on those risk assessments we talked about, will likely be influenced by a bunch of federal regulations and guidelines.
So there are other rules that you need to be aware of.
Right. So for example, if your research is funded by the National Science Foundation, they have these standard terms and conditions that include specific biosafety requirements. And then you have the federal select agent and toxins regulations, which have their own set of requirements for biosafety plans based on the risks associated with those high-consequence agents. And if you're doing research involving recombinant or synthetic nucleic acid molecules, you'll need to consider the NIH guidelines for that kind of work.
So it's not just the BMBL in isolation.
No, it all ties together.
You need to be aware of the bigger regulatory landscape.
Absolutely.
And one last thing on risk assessment. The outline mentions individual susceptibility.
That's an important factor to consider. Some people might be more vulnerable to infection than others due to underlying health conditions, medications they might be taking, weakened immune systems, or even pregnancy. And these factors can increase their risk of acquiring a lab-associated infection.
So it's not just about the agent itself, it's about the person working with it.
Exactly. And that's why it's so important to involve occupational health professionals in the risk assessment process. They can help identify individuals who might need additional precautions or personalized advice.
So constantly reviewing and adapting the risk assessment is key.
Absolutely. The BMBL emphasizes that risk assessment should be an ongoing process. It's not a one-time thing. It should be reviewed regularly, updated based on new information or changes in procedures, and always informed by the latest scientific understanding.
Okay, so we've laid that foundation of risk assessment. Now let's talk about how that translates into actual safety measures, starting with biosafety levels. What exactly are those?
Biosafety levels, or BSLs, are essentially a system of containment levels that describe the specific practices, equipment, and facility requirements for working with different types of infectious agents. The BMBL summarizes those different levels in Table 1, and it's a really handy reference.
So it's like levels of security clearance, but for microbes.
It is. And the level assigned to any particular activity is based on that comprehensive risk assessment we were just talking about. You figure out what you're working with, how you're working with it, and how risky it is, and then you match that up with the appropriate BSL.
So it's not just about the inherent danger of the agent itself, but also the procedures you're using.
Precisely. And ensuring the safety and health of the workers is always coordinated with the IBC or an equivalent body, along with any other safety committees that might be involved as part of their protocol review process.
Okay, so let's say we're working at BSL-2, which is pretty common. Can you give us some examples of what those standard microbiological practices would look like?
At BSL-2, you start seeing those more specific rules that are aimed at preventing exposures. So, for instance, eating, drinking, smoking, handling contact lenses, applying cosmetics, all
Yeah.
of that is strictly prohibited in the lab.
Right, you don't want to be putting your hands near your face or mouth.
Absolutely. And food and drinks have to be stored outside of the work areas entirely. You can't pipette by mouth, you have to use mechanical pipetting devices.
Okay.
And there are very specific policies and procedures in place to minimize splashes and the generation of aerosols. Work surfaces have to be decontaminated at least once a day and immediately after any spills.
Hmm.
All culture, stocks, and waste have to be decontaminated before disposal. And if you're moving any materials out of the lab, they have to be packaged according to all the relevant regulations.
Right, containment.
Exactly. Frequent hand washing is super important, both after handling infectious materials and before you leave the lab.
That's a given.
It is. And when it comes to sharps, like needles and syringes, there are very strict procedures. Used disposable sharps have to go immediately into puncture-resistant containers right there at the point of use. Non-disposable sharps are placed in hard-walled containers that are specifically designed for transporting them to a decontamination area.
Okay.
And you never handle broken glassware directly. You have to use tools like a brush and dustpan or forceps. And again, the emphasis is on doing all procedures in a way that minimizes splashes and aerosols.
Right, reducing those invisible risks.
Exactly. At BSL-2, you also start seeing requirements for things like integrated pest management programs.
To keep those critters out.
Right. And animals or plants that aren't directly related to the work aren't allowed in the lab. Access to BSL-2 labs is restricted, meaning you need permission to enter, and supervisors are responsible for ensuring everyone working in the lab knows and follows those BSL-2 practices.
Okay, so that gives us a good picture of BSL-2. Now let's jump to the other end of the spectrum, to a much higher level like BSL-4. What are some of the biggest differences when it comes to containment at that level?
BSL-4. Wow. That's the highest level of containment.
Yeah, the big leagues.
It is. It's for working with those extremely dangerous and often exotic agents that pose a significant risk to human health. And the differences are significant. For one thing, you see those pass-through decontamination methods, like dunk tanks or fumigation chambers. These are used for decontaminating equipment and materials that can't be autoclaved, and it ensures that anything leaving that high containment area is completely safe.
So nothing leaves without being thoroughly sterilized.
Right. Another big difference is that all liquid effluents from sinks, drains, and autoclaves within a BSL-4 cabinet laboratory have to be decontaminated before being released.
So even the wastewater is treated.
Yes, it's a very stringent level of containment.
Now, the outline also briefly mentions animal biosafety levels, or ABSLs. How do those relate to the standard BSLs?
Animal biosafety levels are basically the animal equivalent of BSLs. They're designed specifically for work involving animals and infectious agents. And just like with PSLs, the specific practices, the equipment used, and the facility requirements are all tailored to the specific risks of the work being done.
So they're kind of like BSLs, but adapted for animal research.
Exactly.
Can you give us some examples of what you might see at a lower ABSL, like ABSL-1?
Sure. ABSL-1 is that basic level of containment for animal work. In an ABSL-1 facility, the director sets the overall policies for biosafety, biosecurity, and emergency procedures. The type of PPE you use would depend on what you're working with, but hand washing after handling animals and before leaving animal areas is always essential. Decontamination of work surfaces and waste is also required. You need an integrated pest management program to prevent infestations, and you can't bring any unauthorized animals or plants into the areas where those infectious materials or experimental animals are being housed or handled.
Right, to avoid contamination.
Exactly.
And what about a higher level, like ABSL-3 with cabinet-level containment? What would that look like?
ABSL-3 with cabinet-level containment, that's where you start seeing some serious engineering controls. In these facilities, any procedure that involves manipulating those infectious animals or materials is done inside a Class 3 biological safety cabinet.
So those are the fully enclosed ones?
That's right, completely sealed.
Yeah.
And they usually have these double-door pass-through autoclaves with interlocks, so only one door can be open at a time. And the outside door can only be unlocked after a successful decontamination cycle.
Oh, wow.
They also often have pass-through dunk tanks or fumigation chambers for decontaminating things that can't be autoclaved.
Right.
And the ventilation systems are really specialized. They've got HEPA filters on both the incoming air and 2 HEPA filters in a row on the outgoing air.
Double filtration.
It is. And they have these airtight dampers that allow the whole cabinet to be decontaminated. The cabinet operates under negative pressure, so if there's a leak, air rushes in rather than out, further preventing anything from escaping.
Wow, so it's like a super secure box within a box.
You got it.
And finally, the outline mentions some really specific building features at ABSL4, which is that highest level. Can you give us a quick rundown of those key elements?
Yeah. ABSL4 facilities are built to an incredibly high standard. It's the top tier of containment. They've got a sealed inner shell, and any openings around doors and things are minimized and sealable for decontamination. All plumbing going through the walls has 2 backflow prevention devices in series to prevent any backflow. Central vacuum systems are generally not recommended, but if they are present, they only serve the contained area and have multiple HEPA filters in line. Ventilation is a dedicated non-recirculating system, and it's got backup fans and alarms to alert staff to any issues.
Oh.
But the incoming and outgoing air are HEPA filtered right near the room, and those filters are tested every year.
Oh.
And the HEPA filter housings are designed so they can be decontaminated in situ. Even the windows are break resistant and sealed. And of course, they've got those double door pass-through autoclaves with special seals and interlocks, similar to what you see in BSL4 cabinet labs.
It really is a fortress.
It is. They think of everything.
Okay, so we've talked about preventing accidental exposures. Now let's shift gears and talk about laboratory biosecurity. How does that differ from biosafety?
Laboratory biosecurity is all about protecting against those intentional acts, that misuse of biological materials, the technology, or even the research-related information. It's about preventing theft, loss, or deliberate release of those dangerous materials. So biosafety is more about those accidents, the spills, the exposures. Biosecurity is more about preventing those deliberate acts of sabotage or terrorism.
So protecting against malicious intent.
That's it.
What are the key elements of a strong lab biosecurity program?
There are a number of really important components. One is personnel reliability. This involves thorough background checks, vetting procedures, and ongoing security awareness training.
So making sure you're hiring the right people.
Exactly. And then you have programs to prevent workplace violence. Sadly, that's something that needs to be considered these days. Training is also essential. People need to understand the importance of biosecurity and know how to recognize and report any suspicious activity.
Okay.
Oversight of dual-use research is also a key part of biosecurity. This involves carefully evaluating research that could potentially be misused for harmful purposes.
Right, that's stuff that could be used for good or bad.
Exactly. Cybersecurity is becoming increasingly important for protecting sensitive research data. And then you have physical security measures controlling access to the lab, having good inventory control systems for tracking materials, and ensuring the facility itself is secure.
So a lot of layers.
It is. And it's important to remember that biosafety and biosecurity are not mutually exclusive. They actually complement each other.
Right, they both contribute to a safer lab environment.
Exactly. Both rely on a well-trained workforce, careful control of materials, good record keeping, emergency preparedness, and overall strong program management.
Now, what are some of the challenges involved in implementing good biosecurity measures? I imagine it's not always easy.
Yeah, there are definitely challenges. One is finding that balance between security and the need for open scientific communication. You don't want to stifle research or collaboration, but you also need to protect sensitive materials.
Oh, it's a balancing act.
It is. And the BMBL suggests a tiered approach to protecting those biological materials based on the identified risks.
So not everything needs the same level of security.
Right. Another important point that the BMBL makes is that in an emergency situation, unless there are specific legal requirements that dictate otherwise, the health and safety of the personnel and the environment take precedence over biosecurity concerns.
So saving lives comes first.
It does.
The outline mentions a 5-step example of a biosecurity risk assessment. Can you walk us through those steps?
Sure. The first step is to identify and prioritize all of those biological materials, the research-related information, and the technologies that are present within the institution. And this includes not only those materials that can reproduce, like infectious agents, but also toxins.
Okay.
You need to document what kind of material it is, where it is, and how much there is. The next step is to think about how those materials could be misused and what the potential consequences of that misuse would be. Based on this, you then rank those materials according to their risk of malicious use. At this stage, the institution might decide that it doesn't even need a separate biosecurity program or that the existing security measures are sufficient. If they determine that additional measures are needed, then you move to the next steps. The third step involves identifying and characterizing potential threats. Who might be interested in stealing or misusing those materials? What are their capabilities? What are their motivations?
So, thinking like a bad guy.
It is, unfortunately. And the fourth step is to identify and characterize any vulnerabilities in the current security measures. Where are the weaknesses? How could someone bypass the existing security? And finally, the last step is to assess the risks by considering both the likelihood of a security breach and the consequences if one were to occur. Then you implement those mitigation measures and constantly evaluate their effectiveness.
So, a very thorough risk assessment.
It is.
Now, how does biosecurity play into emergency preparedness?
That's another important consideration. Lab security policies must address how to handle situations where emergency responders might need to enter the facility because of an accident, an injury, or a security threat. And as we talked about earlier, in those situations, the safety and well-being of the personnel are the top priority.
Right.
So the BMBL encourages facilities to work with their local medical, fire, police, and other emergency responders when developing plans for handling those emergencies and security breaches. It's all about coordination and communication. And standard operating procedures, or SOPs, should be in place to minimize the risk of exposure for those emergency responders. Lab emergency response plans should also align with the overall security plans for the facility, and they should consider a variety of potential scenarios, like bomb threats, natural disasters, power outages, and other facility emergencies that could compromise security.
So, being prepared for anything.
Exactly. You never know what might happen.
Now, training is also essential for biosecurity, just like it is for biosafety.
Absolutely. Training is critical for any biosecurity program to be successful. Lab managers need to establish training programs that clearly define and communicate the roles and responsibilities of everyone working in the lab, from the principal investigator down to the students and technicians. And they need to make sure everyone understands the importance of security awareness, knows those best practices, and knows how to report any suspicious activity.
Right.
Practice drills are also vital for testing those procedures and making sure everyone knows what to do in a real emergency. And the BMBL points out that combining biosecurity drills with existing emergency drills, like those fire drills or those bomb threat evacuations, can be a really efficient way to reinforce those procedures.
So making it a part of the regular routine.
You got it.
Okay, let's talk about another crucial element of lab safety, occupational health support for people working with these hazardous biological materials. What does that entail?
Occupational health programs are essential for anyone working with these potentially dangerous agents. It's not just about treating people after they've been exposed. It's about actively protecting their health and well-being and preventing those exposures in the first place.
So it's proactive, not just reactive.
Exactly. Key elements include pre-placement medical evaluations to assess an individual's baseline health before they start working with a particular agent, periodic health assessments to monitor for any changes in their health, providing the necessary immunizations or vaccinations, having clear plans for managing exposures if they do occur, and implementing medical surveillance programs for those working with specific high-risk agents.
So monitoring their health over time.
Right.
And what happens if a lab worker does experience an exposure incident? What's the role of the occupational health professional in that situation?
If someone is exposed, the occupational health provider steps in immediately. Their primary responsibility is to do whatever they can to limit any further harm to that individual. So, depending on the nature of the exposure and the agent involved, this might involve things like providing post-exposure prophylaxis, monitoring for symptoms, and providing supportive care. They also play a crucial role in documenting lessons learned from these incidents. This helps identify any systemic issues that might have contributed to the exposure and helps improve safety protocols to prevent similar incidents from happening again.
So turning a negative into a positive.
It is. It's about learning and improving.
The outline mentions the concept of clinically oriented post-exposure risk assessment. Can you explain what that means?
So when a lab worker has a potential exposure, the clinician needs to assess the risk, and it's a two-pronged approach. They look at the risk of exposure, or ROE, which is the likelihood that the person was actually exposed to the agent, considering the circumstances of the incident. And they look at the risk of disease, or RADA, which is the likelihood that the exposure will actually lead to an infection, taking into account things like the pathogenicity of the agent and the person's individual susceptibility. This helps them make informed decisions about what medical interventions might be necessary.
So it's a way to guide those treatment decisions.
It is.
And what are some of the things to consider when it comes to post-exposure testing?
The best approach to testing really depends on the specific pathogen involved, the type of illness it causes, how reliable the available tests are, and the individual's risk factors. It's crucial to remember that waiting for lab results, including pregnancy tests, shouldn't delay starting any post-exposure prophylaxis, or PEP, if it's deemed medically necessary. Sometimes PEP, like antiretrovirals, requires specific baseline lab tests to be done before starting treatment. It's often helpful to get a baseline serum sample at the time of the incident because it can be used for comparison later on. But routinely testing for pre-existing infections with the agent of concern isn't generally recommended unless there are specific clinical indications. And if there aren't any symptoms of infection, doing additional tests to see if transmission occurred is usually not necessary. However, if early detection of asymptomatic infections is beneficial, like with Hep C, post-exposure testing should be done in a way that maximizes the chances of catching those early infections, like using PCR tests to detect viral RNA even before antibodies are detectable. For antibody tests, comparing the results from two blood samples taken at different times is much more reliable than relying on a single test. The first sample is taken as soon as possible after exposure, and the second sample is taken later when those immune markers are expected to be detectable. Blinding the lab that's processing the samples to the timing of collection can help reduce bias. A documented seroconversion, meaning going from a negative antibody test to a positive, or a significant increase in those antibody levels along with a compatible illness, is usually pretty strong evidence of a recent infection. The timing of those repeat blood draws can be adjusted based on the specifics of the exposure, how the agent behaves, the person's overall health, and any medical countermeasures that were given. For example, if you test too soon after exposure, you might miss those early immune responses, so repeat testing at appropriate intervals might be necessary. And that's especially important with agents like human retroviruses if PEP was given or if the person has a compromised immune system. If a research test that's not yet standardized is being used, it's good practice to include those negative controls from uninfected sources, positive controls if you can, and to blind the testing lab to the source of the samples and when they were collected. It's also important for the healthcare provider to clearly